Bismillahirrahmanirrahim. Assalamualaikum and very good morning. So in this topic we are about to discuss on two types of filters, which are the Butterworth and also the Chebyshev. So basically you have learned this, or you have seen these two types of filters in signaling system and also in communication principle. So perhaps this will enhance your understanding on the filter operations. Okay, just a quick overview on a filter. So basically it's a network. Okay, when there's input, a system and output, it is in network configuration. Okay, so it provides perfect transmission for signal with frequencies in certain passband region and infinite attenuation in the stopband region. Okay, that's basically the definitions of a filter. So for RF microwave signal, basically it consists of the desired signals and also the noise or unwanted signals. Okay, the desired signal usually lies within the specified frequency bands, while the noise or unwanted signal lies within the outside of the desired frequency bands. Okay, so the filter have two important bands or region. So obviously it has the passband and also stopband region, in which in passband region the frequency range is where all signal lies within the passband region will be chosen or will be filtered in, while the signals lies within the stopband area of frequency bands within the stopband area will be rejected. Okay, basically the filter is characterized by using a transfer function, so in which it is basically the ratio between the output over the input. Okay, so and you have also learned how to characterize or how to analyze the filter characteristic by using a dot plot in signal and systems particularly. Okay, and the attenuation can be calculated by -20 log of your transfer function, the ratio of the output over the input. Okay, and next is the difference between the passive filter and also an active filter, in which the output power of passive filter will always be less than the input power. Okay, the output at this point will always be less than the input point. Okay, so because during transmission, if you remember, there will be a coupling, there will be disturbance, there will be signal loss due to the reflection and also retransmission across the junction and etc. Okay, that's why in passive filter, the output is always larger than the output is always lesser than the input. Okay, while in active filter, the output could be higher, or at least more or less equal to the input power, because the active filter allows power gain, okay, in which amplifier may be added into the system so that the power may be enhanced at the output point to ensure that the signal at the output point can be recovered. Right, so this is another revision. So a passive filter characteristic. So for low pass filter or LPF, okay, it transmits all signals within the passband region. So this will be your passband region. Okay, and some upper limit of omega c, so sum of this part, and attenuate all signals within frequencies above omega c. So the outside passband region will be rejected. Okay, next the high pass filter. Alright, so this is the low band low pass area. So for high pass filter, it allows the signals or choose the signal within the passband region and some part of the signals in between the omega c to the stop band frequency, and reject signals in this area. Okay. And next is the band pass and band stop filter. So for band pass filter, it passes signal with frequencies in the range of omega 1 to omega 2, or from f1 to f2, and reject frequencies outside this range, while the band stop filter is basically the complement of the band pass filter, where it rejects the signal within the specified frequency band between f1 and f2. Right, so for band pass filter BPF, so the signal lies within f1 and f2 will be selected or will be chosen, while for band stop filter the signal lies within the same frequency band f1 and f2 will be rejected. Okay, only the signal in this area will be chosen. Okay, let's look at the filter response. Okay, basically, as I mentioned earlier, it is a linear two-port network, okay, that provides transmission of signal within the passband region and reject the signals outside the region or in the stop band area. Okay, in passive filter analysis, okay, usually the filter will be characterized by using the transfer function, in which it is basically the ratio Hs or Hg omega, the ratio between the output over the input. Okay, so and also it can be analyzed by using the attenuation or the ST1, and the ST1 is also known as the gain or insertion loss analysis. Alright, so the value on the y-axis here is the linear value, and if it is in dB, it is 0 dB or negative 3 dB. Okay, so negative 3 dB is where the power has been reduced by at least 50%. Alright, and the bandwidth is measured across the 3 dB lines. So for example, here is f1 and here is f2. So the bandwidth is basically f2 minus f1. Okay, so the 3 dB point here is also known as the break frequencies, or the FC or omega c. It's the cutoff frequency point. For example, if you have a low pass filter, so 0 dB and minus 3 dB. So this is where your cutoff frequency is. Okay. And what else? Okay, this is the passband region, okay, where the signal will be selected. So in this case, this is the band pass filter. Okay, if you have the low pass filter, so this will be your passband region, and outside of this will be your stop band region. So the cutoff frequencies is the frequency at which the voltage gain A equal to 0.707 or 3 dB of its maximum value. Okay, so as I mentioned here, at 3 dB point, so where your cutoff frequency or the break frequency is. Okay, so the bandwidth, the stop band. Okay, so that's it. So depending on different types of filter, you will be having different types of filter response. Okay, you can refer to the earlier slides where you can see different types of filter response depending on different types of filters. Okay, next let's look at the difference between the Chebyshev and Butterworth filter response. So the red lines represents the Chebyshev filter. So this one, okay, representing the Chebyshev filter response, while the blue lines represents the Butterworth filter frequency filter response. All right, so the Chebyshev, okay, so the criteria or the characteristic of these Chebyshev and Butterworth are listed in the table. So Chebyshev having ripples in the passband area, okay, and some of it having the ripples in the stopband area as well. And the Butterworth is flat top, okay, there's no ripple at the passband area. So this one, the blue lines is flat top. This is for Butterworth. Okay, and the width ripple, it is the Chebyshev. And then it's fast roll off for Chebyshev. Okay, it has the ripple and then it suddenly drops down. So this is what does it mean by fast roll off, or it has higher transition. Okay, so in between the passband area to the stopband area. Okay, while the Butterworth is having a slow roll off. Okay, the lines drops down. The transition between the passband to the stopband is a bit slower. Okay, it's a bit linear. Okay, and then if you have higher filter order number, then you'll be having steeper lines. Okay, if you have, for example, n equal to 1 versus n equal to 5. So you'll be having, if you have n equal to 1, so the lines will be looking something like this. But if you have n equal to 5, then you will be having steeper roll off. Okay, and in terms of the circuit generation or circuit development, the Chebyshev having simpler circuit generation, while Butterworth having complex circuit generation or development. And lastly, the Chebyshev is also known as equiripple, while the Butterworth is also known as maximally flat. Alright, so this figure representing a different filter response for the same filter order number. So n equal to 5. Okay, so look at for the maximally flat or the Butterworth. Okay, with flat top in the passband area and the equiripple for Chebyshev in the passband area. Okay, let's see some of the practical design of filters. Okay, this is an example of a low pass filter, a printed one. Okay, so this is the design in the simulator, in which the calculation has been performed so that you can calculate the dimension of the structure and also the length of this transmission line. So this is the fabricated one. Okay, the realized low pass filter, a printed RF circuit of the low. Okay, next, another practical implementation of the filter design. So again, another low pass filter for Butterworth. So the first step is to get the circuit realization from calculation. Then you'll get the filter order number. Then you determine the normalized elements or the components in your filter circuit, and then get the design into your simulator. Perform the simulation and to check whether the filter performance as required or not. And then if everything is okay, then you may fabricate that before the final production. Okay, so here the transformation from circuit to physical PCB layout. Okay, these are another types of practical filter. For example, the waveguide filter. So waveguide, when you have a hollow tube, metallic hollow tube, and then you have filter, so in which you can control which port to be used and etc. And then so you can set which signal to be passed through and reject. Okay, and then commensurated line low pass filter, and this one is parallel couple line band pass filter. So different configuration may affect the performance of the filter, okay, according to the specification given or the intended output the designer wanted to achieve. Okay. Okay, so these are another examples of filter designs. Okay, same goes to this one. So different types of filter or different specification may result in a different configuration. So you may use a different shape, different structure, different component and element depending on the specification you have. Okay, so depending on what types of application and also what types of signal you are about to achieve. So lastly, this is the coaxial low pass filter. So that works at 1296 megahertz. So you may find more example of filter design, low pass, high pass, band pass, and band stop filters from other references. Okay, next, let's look at the filter circuit realization. So I believe that you have seen this in signal and system course. So in which the first step, the most important part, is to determine the order number, the filter order number. So either by using equation, by calculation, or by referring to a graph. Okay, I believe in signal and system you have seen these two equations to calculate the Chebyshev and Butterworth filter order number. So in which once you get the end, you should round it up to the next higher whole number. Okay, if for example 1.05, then your n should be equal to 2. Okay, why you need to consider higher number? It is to make sure that the remaining part of this will be filtered in as well, because some information may be included in this smaller region. Therefore, to account for a complete transmission, you need to round up the n, the filter order number, into the next higher whole number. Okay. Next, after you get the filter order number, you need to normalize. You need to design a normalized circuit low pass filter. Okay, low pass filter circuit, it is in normalized values, in which you need to refer to a table representing how many elements or components you need to consider in order to get the circuit, normalized circuit for a low pass filter design. Okay, depending on whether it is equiripple, Chebyshev, or it is Butterworth maximally flat. Okay, after you get the normalized circuit, then you need to transform the normalized low pass filter circuit in step 2 into the required type of filter. Okay, for example, obviously from the second step, you will get the low pass filter design. So in this course, the normalized circuit is basically in for low pass filter. Okay, then to get the high pass filter, for example, then you need to perform transformation, okay, circuit transformation, to get the high pass filter. So some of the components may be calculated by using specified equations so that you can get the actual values of the final circuit design. Okay, lastly, the implementation with slump element or planar element. Okay, so this is in the next design process, in which we will cover just up to the third one. Okay, so the implementation require further analysis and also simulations. Okay, for step 1, to calculate the filter order number, either you can use the equation okay, depending on types of filter you have or you are about to design. But if you don't have the equation, you can use the graph, the attenuation versus normalized frequency graph to get or to estimate the filter order number. Okay, so and you need to make sure that you refer to the correct graph. Either it is for maximally flat, meaning that this graph is only for Butterworth filter design. Okay, first you need to get the x-axis representing the omega divided by omega c minus 1, in which omega here is actually the omega s over omega c minus 1. Okay, the stop band frequency. Okay, once you have the stop band frequency, okay, then you will drag the lines up to the attenuation, the stop band gain. For example, you get n equal to in between 3 and 4. Okay, for example, n equal to 3.5. So to get the actual n, you need to make sure that you round it up to the next higher whole number. Therefore, the n equal to 4. Okay, same goes to when you have a Chebyshev or equal ripple filter to be designed. So again, the same steps. So it is omega s over omega c minus 1. Then you'll get the filter order number. Okay, and it depends on how strong the ripple is. Okay, it's either 0.5 dB or 3 dB ripple. So 3 dB ripple meaning that you have very high ripple factor. Okay, 0 to 3, meaning that about 50% of the power already being used to transmit the ripples signals here, in which basically most of the information could be just included in just a flat top one. Okay, for example, so it is not favorable 3 dB. Okay, try to avoid that. So it will be better to use 0.5 dB, just 0.5 dB ripple for Chebyshev filter design. Okay, let's look at a quick example. Okay, this is to compare the filter order number if you calculate that using an equation or if you use a graph. Okay, design a Butterworth low pass filter with omega c equal to this value. So Butterworth is flat top, low pass filter. Okay, and the omega c, as you know, it is at 3 dB attenuation. Okay, and this is where your omega c is, so it's 11.25 radian per second. Okay, and then a pass band gain in between 1 to 0.891 or minus 1 dB for omega equal to 0 up to 10. Okay, here is 11, so 10 is somewhere here. So this is pass band, I'll call it omega p, the pass band frequency. It is equal to 10. So this is basically your main pass band area, and some of this will be accepted as well. Right, and the gain is from 0 to minus 1. Okay, somewhere here before it drops down. It starts to drop down something like this. Okay, here. And then a stop band not to exceed minus 30 dB. Okay. Minus 30. And here is your omega s equal to 20 radian per second. And the gain or the attenuation is minus 30. This is your alpha s, and this is your alpha p, and this is your cutoff frequency, cutoff value. Okay, so design a Butterworth. So the steps to design: first you need to get the filter order number, and then get the normalized circuit and get the transformation. Okay, so let's simplify or summarize the parameter that you have. So the types of filter is low pass filter, and it is Butterworth or flat top or maximally flat, and the passband frequency as shown up to 10 radian per second, and the passband attenuation is 1 dB, okay, less than 1 dB, and then the stop band frequency is 20 radian per second, and the attenuation is 30 minus 30 or minus 30 dB. Okay, so let's look at how to calculate the filter order number. Okay, so first step is to calculate the n. If you have the equation in hand, then you can just use the equation straight away, or else you can refer to the graph if it is provided. Alright, so from signal and system. So if you still remember that the alpha S and alpha P in this equation need to be in dB positive value only. Okay, for example, alpha S here, so it's log 10 of alpha S. So alpha S is 30 dB, so just put 30 divided by 10 minus 1, okay, and divided by 10 of alpha P. Alpha P is 1, so 1 divided by 10 minus 1. Okay, and then this one divide by 2 log of omega Sn. So omega Sn for low pass filter is omega S over omega P. Okay, so omega Sn equal to omega S over omega P. So omega Sn for low pass filter, so omega S in this case is 20 divided by omega P is 10. So omega Sn equal to 2, right? So here equal to 2. And then after the calculation, you will get n equal to 5.9569. So in which you need to round this up to the next higher whole number. So basically the n is equal to 6. Okay, let's look at how to use the graph. Okay, please make sure you use the correct graph. In this case, it's Butterworth, so make sure you use the maximally flat filter response or filter graph, attenuation graph. So then you need to refer to the x-axis here. Okay, so omega here representing the omega S over omega C minus 1. So in this case, your omega S is equal to 20 divided by your cutoff frequency given in the question is 11.25 minus 1. Then once you get the value, then you drag down the lines across the attenuation value. So attenuation value is 30 dB. Then you get the n. Right, so omega S divided by omega n minus 1, so omega Sn is 0.77. Look at the x-axis, 0.77, 0.7, 0.77 somewhere here. So draw the lines across 0.77 and then crossing with the attenuation of 30 dB. Okay, 30 dB, so you get your n is somewhere here. So n is between 5 to 6, then make sure you choose the higher whole number. Okay, in this case it is equal to 6. Okay, so if you compare the calculation using equation with the graph, you'll get equally the same. N will be equal to 6 in this case. Okay, next, once you have calculated the filter order number, then you need to get the normalized low pass filter circuit. So you can choose either to use this configuration, configuration 1, configuration 2, or configuration 3. You can choose either one. Okay, unless the question or the specification given requested for certain configuration. Okay, so for example, if you choose the first configuration, so the first component will be in shunt or in parallel. So the value is represented by C1 or G1. Then you need to refer to the table for the specific n. For example, just now n equal to 6. So n equal to 6 in here. So these are the values of the component that you should include in your design for the normalized circuit. So in this case, the first one, if you use the first configuration, the first one is capacitor. Okay, so the first value is G1 for capacitor. Then it is 0.5176. So here, for example, so you have, okay, let's draw this one. If n equal to 6, the first component, the resistor and the load, will always be normalized to 1. Okay, so the first one, this one is fixed, so R not equal to 1. So the first one is the capacitor C1, so 0.5176. Okay, followed by the inductor, and again another capacitor. So C1 here is L2, so L2 will be using the next value 1.4142, 1.4142. Next, followed by the third component C3, it's 1.9318, and then another inductor L4. Okay, put the values in 0.93, and then you still have fifth component, okay, C5, 1.4142, and then you have another inductor L6. Okay, this is the L6 value, and the lines will be terminated by the load impedance. Okay, R equal to, this one equal to G7, sorry, this one n plus 1. In this case, if n equal to 6, so the last one is G7. G7 or the values, this is if you have other filter order numbers, then you'll have C7. But if it is just up to 6, then the last one will be terminated with the load impedance. So it's always equal to R not equal to 1. Okay, so this is how the normalized filter circuit is designed. Okay, same goes to when you have to design the equiripple or Chebyshev filter, meaning that you need to first look at the ripple factor. Okay, if it is for 0.5 dB ripple factor, then you refer to this table. Otherwise, you need to refer to the second one, and then refer to your n. For example, n equal to 6, then get your values. Okay, the same configuration, whether you want to choose configuration 1, 2, or 3. Okay, after you get the normalized circuit, okay, then you need to perform the to get the final circuit, or to get the actual circuit design, in which you need to recalculate the value of the components, okay, the actual components. So, and it depends on either the final design must be in low pass, high pass, band pass, or band stop filter configuration. Okay, so in the second step, you will design a normalized low pass filter. If the system require you, or the project require you to design a low pass filter, then you can use the same configuration. Okay, but the components value must be recalculated depending on the filter transformation equation. Okay, so if you want to design, the final design must be in low pass, then the serial inductor must be recalculated by using this equation. Z0 is the characteristic impedance, so L the inductance values, and then omega C the cutoff frequency. If you have the first component is the parallel capacitor, then you need to recalculate by using this equation. If, for example, the system requires a high pass filter, okay, then you need to transform the normalized circuit in step 2 to a high pass filter. Okay, the first one will be the high pass filter in the first component for serial capacitor. So you need to get the actual value or the final value by using the following equation and so on. Okay, if you refer to the band pass and band stop, there's a square here. Okay, that's basically representing the fractional bandwidth in which you can calculate by using the difference between the higher frequency minus the lower frequency at the passband area at the minus 3 dB point divided by omega naught. Is the frequency of intention, okay, or it's basically the center frequency of the system. Okay, so omega naught, the center frequency, equal to the higher omega plus the lower omega divided by 2, or you can also use this equation. Okay, I'll continue with normalized circuit realization and also the circuit transformation in the second video. Thank you.